Hello, everyone. I'm Mina.
Hi, I'm Alex.
Hi, my name's Lucia.
And I'm Jacob.
And we are Team Exollent. We have come up with an experiment that would test the precision of the simulated Canadarm2 based on task complexity. The simulated arm needs to be precise and accurate so it does not damage the stations outside and the astronaut operating with it. We considered that the Canadarm2 is a 17-meter robotic arm that helps guide astronauts outside of the space station. We aim to use both on the ground station, NASA, and International Space Agency, and on the space station itself. For our experiment, we used 4 University of Michigan undergraduate engineering students, ages 17 to 19. We hypothesized that using the Canadarm2 at a slower speed, with lower task complexity, will result in fewer errors, making it more precise. Using the telerobotic arm at a slower speed will allow the astronaut to reach the destination faster at the desired angle, decreasing the chance of making errors.
Now I will go over the design of our study. The independent variable for our study was the complexity of the task. In order to implement this, we operated our simulated arm at different tempos, with a higher tempo corresponding to a higher complexity. This was predicted to affect the precision of the subject's movement, as well as the reaction time and comprehension. We have already discussed why precision is an important aspect to consider. As you can see here, the environment the Canadarm2 operates in is very complex and there is little room for error. However, we have also chosen to study the user's reaction time and comprehension in order to simulate the intense communication and situation awareness that would be needed to operate the arm in real life. The primary task in our study was to move the model Canadarm using the exoskeleton system. This was done to measure the variable of precision. We had each subject use the exoskeleton arm to attempt to reach a target of 120 degrees. The actual angle the subjects reached during each movement was then recorded to find the variance, which is an indicator of precision. Each subject performed trials where they moved at 2, 4, or 6 beats per minute, with 2 beats per minute being the most complex and fastest movement, and 6 beats per minute being the least complex and slowest movement. While performing this movement task, the subject also performed the secondary task of responding to a researcher. The subject was told a color or shape. Then they had to respond with the correct corresponding color or shape from the list shown here. For example, if the researcher said yellow, the subject should respond with circle. Success in the secondary task was indicated by the number of correct answers a subject could give per second. Here we see a flowchart summarizing the reasoning behind the study's design. We increased the task speed to implement an increase in complexity. We expected this increase in complexity to lead to a higher variance during the primary movement task and fewer answers per second in the secondary task. A higher variance indicates a lower precision, which in the real world could lead to a decrease in safety and reliability. Fewer answers per second would indicate a decrease in the subject's comprehension and reaction time, which in reality could lead to a breakdown in communication or a lack of understanding of the situation.
The simulated arm that was used in the study was constructed using 2 1/2-inch by 3/4 inch by 8-inch wooden beams, one 1-inch by 4-inch by 10-inch wooden beam, an L bracket, a hinge, screws, and hot glue. The arm was constructed as shown in these pictures, such that the 2 smaller beams of wood were connected with the hinge, with one beam attached to the larger beam, and the other beam was allowed to swing freely. This design simulates 1 degree of movement of the Canadarm2. The exoskeleton that was constructed for this study consisted of a servo motor attached to a corrugated plastic strip with a loop of Velcro attached to the end. The servo motor was glued to the simulated arm about 2/3 of the way up, and the Velcro was looped around the hanging beam of the arm. This video clip shows the exoskeleton in action. When the goniometer is moved, the servo motor rotates the corrugated plastic strip, which in turn moves the Velcro loop along the simulated arm. This motion causes the arm to extend and contract with the motion of the goniometer. This design of the exoskeleton was chosen because of its simplicity to build and small amount of possible failure points. This design models a possible system that could be used to operate the Canadarm2.
In order to find the preciseness of our data set in our primary task, we can calculate the variance. Variance measures how far a data set is spread from the average value. It's notated as the square of the standard deviation. The formula for variance is shown on the screen. First, calculate the average of the data set. Then take the difference between the mean and each data point. Square this value and take the sum of all the squared values. Divide this by 1 less than the number of data points. High variance indicates low precision and decreased performance, while low variance indicates high precision and increased performance. For our secondary task, we will be calculating the number of correct answers per second. The formula for answers per second is shown on the screen. Take the total number of correct answers and divide it by the duration of task in seconds. The primary task results are shown on the screen. This shows the average angle measurements of the participants for the 3 different tempos and the variances. Here, figures 3 and 4 are shown. Figure 3 shows a bar graph of average angle measurements in degrees for 3 different tempos. One standard deviation of each tempo is shown in the lines above the bars. Figure 4 shows a line graph of variance for 3 different tempos. The secondary task results are shown on the screen. This shows the average correct answers per second for the 3 different tempos. Here, figure 5 is shown. Figure 5 shows a bar chart of the average correct answers per second for the 3 different tempos. In our introduction, we hypothesized that lower speed and lower complexity of the Canadarm2 will result in low variance and therefore high precision, and vice versa for higher speed and higher complexity. Similarly, in the context of this study, we predicted that moving the arm at a lower speed would allow for low variance and higher precision in reaching the desired angle and higher accuracy shown by correct answers per second. And of course, vice versa for higher speed. Let's go back to Table 1. We can see that the fastest tempo, the 212 tempo, had the highest variance of 22.5, and the slowest tempo, the 616 tempo, had the lowest variance of 3.1944. In fact, we can see a trend here. As the speed of the tempo decreases, the variance increases. And since high variance indicates low precision and low variance indicates high precision, we concluded that the 212 tempo had the most insufficient precision and the 616 had the highest. This supports our hypothesis from earlier that lower speeds result in higher precision.
With the 414 tempo being closest to the average, it does not necessarily make it the prime candidate. The 414 tempo has a higher variance, making it more susceptible to low precision and accuracy than the 616 tempo. The 616 has more precision and accuracy throughout the trials. It also showed the lowest variance, while the 212 showed the highest. The higher the variance, the harder it is to hit the exact value, making it easier for a mistake. Looking back to Figure 5, there were more correct answers answered and the 616 tempo than any other tempo. That is evident that our hypothesis is correct.
Let's now go back to Table 2. We can see that answers per second increased as the tempo increased. The fastest tempo, the 212 tempo, had the lowest rate of 0.239 answers per second, whilst the slowest tempo, the 616 tempo, had the highest rate of 0.258. This is likely due to the increased amount of time between each stop to coordinate and answer the questions correctly. This also supports our hypothesis from earlier that lower speeds result in higher accuracy.
This study had multiple limitations. First, the simulated arm only had 1 degree of freedom, whereas the Canadarm2, which the arm was supposed to simulate, has 7 degrees of freedom. This would make the primary task of the study much simpler than the actual task of the astronauts operating the Canadarm2. Another limitation was the fact that the simple questions of the secondary task would be much easier to manage than the conversations the astronauts would be having with other crew members or mission control. Another limitation of the study was the fact that the number of participants was small and all from the same relative demographic, that being University of Michigan freshman students with little to no experience with robotic arms like the one simulated. Also, since the participants hadn't used the arm much prior to the study, it is likely that throughout the study, the participants were getting used to the arm, which could affect the results of the study.
Besides simply fixing some of the limitations we have already discussed, there are many other ways we could expand upon this study. In our results, we found that there was a much greater increase between the 212 and 414 motion than between the 414 and 616 motion. This indicates that there may be a certain complexity at which our precision will begin to decrease dramatically, a precision drop point, as shown in the blue graph. This same study could also investigate whether a similar drop in precision occurs when the complexity of the task is too low and the subject possibly loses focus, as shown in the green graph. It may also be important to consider if we can push the complexity higher if we train our participants beforehand. For example, if our subjects had extensive practice before testing, would we have seen a smaller variance in the 2-1-2 motion, more similar to that of the slower motions? Would we have instead found that the training precision drops at a faster tempo, such as a 1-1-1 tempo? In this study, we chose to increase complexity by increasing the speed of our subject's movement. But there are many different ways we could have done this. We could have compared variance when the subject switched their non-dominant arm. We could have inverted the controls so that an extension of the subject's arm caused the model arm to close. Or we could have introduced a delay between when the subjects moved and when the Canada arm moved. A delay would be especially interesting, as a delay would likely exist if the Canada arm was being controlled from Earth. We could see how these relationships between different implementations of complexity and precision compare, so we can be aware of what may cause the most problems when using the real Canada arm. We could also see how other important aspects, such as accuracy and stability, are affected by these complexities.
As the task became more challenging by answering the questionnaire, which had the subjects connect colors to shapes and vice versa, the desired angle value's accuracy started to decrease, along with the precision. Referring back to the hypothesis, we were correct because the more time we had to reach the desired angle, the closer we got, making it more accurate and precise compared to a faster tempo. The 616 tempo had the lowest variance, and the 212 had the highest variance. When operating the telerobotic arm, it is essential to work at a slower pace to make the movement more precise to the desired angle, and to make sure the astronaut is not in danger on the Canadarm2, especially when given a task that is considered more intricate.